So what I wanted to talk about today was the relationship between worker knowledge and system integrity and safety. The topic of the presentation is specifically related to onshore infrastructure, natural gas infrastructure, although the concepts really are applicable to any type of infrastructure. A couple of definitions that I want to start off with. The term system integrity or integrity management, we use that term to refer to the structural health of the assets, making sure that the gas stays in the pipe and doesn't leak out. And then safety, I'm not referring to personnel safety in terms of like health and environment safety, but public safety. Natural gas is an explosive material, and when it does get out of the pipe, it can be very dangerous. So when I use the term safety, it's related to the integrity management of the pipe and public safety. So what I'd like to do is talk about the U.S. experience in terms of the integrity of our natural gas infrastructure and how that relates to worker knowledge. So I'll talk a little bit about some of the trends that we've been seeing over the last couple of decades, and then I'll talk about the three solutions, or the three components of the solution, which would be a combination of regulations, quality control programs, and technology. So this picture gives an overview of the way that the natural gas value chain is structured in the U.S. This is the same one that I put up yesterday, but what I'll talk about now is the way that it is regulated. PHMSA, which is our federal regulator, has overall responsibility for the gathering lines, high-pressure transmission lines, and the lower-pressure distribution systems. They provide regulations, and then the states can put additional regulations on top of the federal regulations. So I mentioned PHMSA because what they do is they collect statistics on any incident that happens. And an incident, there's a specific definition of it, but it basically means any time that a natural gas pipe leaks and causes some sort of damage, either to people or to property. So every time there's an incident, PHMSA collects data on the root cause of that incident as well as the consequence of that incident. And this, the graph on the upper right-hand corner shows the overall number of incidents in the natural gas industry over the last 20 years or so. It's not exactly going down. Despite the fact that there's been a lot of safety regulations put in place over the last 15 years, about every 2 years we add a new integrity management regulation. So the trajectory of the regulations has been going up, but yet our incidents haven't been going down. And I would argue that it's not because the regulations aren't working, but it's simply because our infrastructure is aging. Some of our high-pressure transmission pipes are 70 years old. And these are operating at very high pressures. And we even have some pipe that's about 100 years old, some of our cast iron in some of our urban areas. And there's just no way to have an infrastructure that old and not have leaks that result in incidents. So digging a little bit deeper into what actually causes these incidents, you can see the pie chart on the bottom right-hand side there, and it gives the root causes as reported by the operators. One of the biggest causes of damages and incidents is excavation damage. That's excavators hitting the pipe underground with a backhoe or some type of excavation equipment. The other leading causes are corrosion, and something that's really disturbing to me as someone that tries to use this data to figure out what types of technologies can solve these problems is this other category. That means that they don't know what caused the incident, or they just didn't do a good job of investigating it and reporting it. And I'll talk more about some of the implications of this other category. But the one that I specifically wanted to focus on was this category called incorrect operations. So that means a worker did something wrong, and that's what led to this incident. Now, if you think about it, I'd really like to have a good definition for what that means, what that encompasses, because if you look at all of the other root causes, like corrosion or weld failure, almost all of those you can tie back to someone at some point doing something wrong. Maybe corrosion was the result of someone not hooking up the cathodic protection system, and so then 3 years later it corrodes away and causes a leak or an incident. Is that a corrosion failure, or is that incorrect operations? Or if someone makes a poor weld, is that a weld failure, or is that incorrect operations? Digging a little bit deeper, this is another data collection initiative that we have in the U.S. It's specifically related to plastic pipe. This is a voluntary industry-led data collection initiative, and they take a much more granular look at the root causes. And what this chart up here shows is that installation error, which means a worker did something wrong, is the leading cause of most failures. Again, you can see that other and unknown are a significant portion of the root causes, so that's obviously a problem because it really masks what could actually be some trends that we're seeing. But if you take the other and the unknown away, installation error is in the top 1 or 2 leading causes of plastic pipe failures, and specifically related to joints. If that's the fusion process of attaching fittings or putting pipes together, almost 60% of all failures on joints are related to the operator not doing that thing correctly. One of the other things that we've identified as part of this data collection initiative is that failures are increasingly occurring during the first 5 years of that asset's life. That also points to the fact that installation error probably has a lot to do with why these assets are failing. If it occurs 20, 30, 40 years down the road, then you can blame it on the materials or on some sort of external factor. But we're seeing a big spike in the amount of assets that fail within the first few years of being installed. So why are we experiencing these increased rates of operator error related failures? Accelerated replacement programs. That's the term that we use to describe replacement programs. Like I said, a lot of our infrastructure is very old. It's between 50 and 100 years old in a lot of urban areas, and there's big, huge construction projects going on all across the country. In Chicago, where I'm from, for example, there's a $2 billion, that's B with a billion, $2 billion program to replace the aging cast iron pipe over a 10-year period. So we're talking about hundreds, maybe even thousands of miles of pipe that is being upgraded, and it's all being done in a very short amount of time. So that's a lot of construction activity. That's a lot to keep track of. And the combination of this increase in the rate of construction combined with the knowledge loss that we talked about yesterday really leads to strain on resources and capabilities and skill sets. We're also seeing a dramatic increase in the use of contractors that actually perform these installations. And while that's in itself not necessarily a problem, it can be a problem if you don't have the proper oversight. And we're also seeing a decrease in the amount of auditors and inspectors that are being deployed to monitor the quality of the work that these inspectors are doing. All right, so what are the potential solutions to this problem? What I'm going to propose is that it's 3 things. It's regulations, smart regulations, quality control programs at the infrastructure operators, and then technology. So in terms of regulation, in the U.S. we have a very dynamic set of regulations. Some of them are very detailed and specific, and they're very prescriptive. The government will tell you what type of technology to use and how often you have to use it. Other regulations are very high level and general. That leaves a lot of room for interpretation. And the regulations around the skilled workforce and the quality of the work that's being done, I would use this as an example of these high level general regulations. Basically, the regulations just say for certain tasks that impact the integrity of the pipe, operators have to have a process for qualifying the workers that perform work on those specific tasks. That's really about it. So there's obviously a lot of room for interpretation there. The government does provide implementation guidelines and FAQs, frequently asked questions. So that's their way to provide more guidance to the industry about how to actually comply with these regulations. One of the kind of unintended consequences of this, the operators ask for these high-level, flexible regulations, but then when they get them, sometimes they're not happy with the result of the government audits. And what I mean by that is if you have these high-level prescriptive regulations and then the government sends out auditors to make sure that the industry is complying with them, you might get someone who's fairly relaxed and just comes and looks at stuff and says, yeah, that's good. But then you might get someone that's a Six Sigma quality engineer that's been doing this for 30 years that wants to see extensive documentation and might have a completely different understanding of what these regulations mean. So to address that, the government has provided inspection protocols that are guidelines to try and provide some consistency about what it means to make sure that these operators are really qualified to do this work. Quality control programs. So these are the internal programs that a infrastructure operator would use. Again, the use of contractors has really changed the dynamic of the type of quality work that's needed. A lot of operators are going to this, what they call multi-layered approach. And what that means is they're moving away from using formal auditors and looking at pushing the level of accountability further down. And that's good. I mean, you definitely want to have various levels of responsibility throughout the organization. You want the contractors to have their own level of quality. You want the foreman to have a certain level of quality, and then you can have some formal inspectors on top of that. The regulators haven't necessarily had the same perspective on that. There's definitely been some criticism about the fact that some of these integrity programs are too informal and they're too sparse. There's no regulations on the number of job sites that have to be inspected. Some companies do 1%, some companies do 10%. Sometimes it varies just based on the number of inspectors that they have available that day. So what I was really interested in talking about is how technology can help fill this gap. So you've got all this construction going on, hundreds of miles being installed every year just by one company, and it's obviously a strain on resources, but you need to make sure that the assets get installed properly because it has integrity impacts for these assets that are carrying a flammable, combustible material and going underneath people's houses, and they're going to be in the ground for 50 to 100 years. So you need to make sure that when they're put in the ground, they're put in the right way that will protect public safety. So the way that I look at this technology, it has a couple of jobs in terms of quality control and making sure that field crews do the right thing and follow company procedures. One way to think about technology is that it provides incentives for people to do the right thing. If they know there's some sort of technology out there that's monitoring them, it just raises their level of awareness and just keeps them on their toes and allows them to do their best. It's also what we found technology can also be used to catch mistakes that people didn't even know were mistakes. Maybe they thought that's the way that it was supposed to be done, but technology can be a way to identify those. Technology can also be very cost effective. People are expensive. Sending inspectors out can be very expensive. How can we use technology to reduce the cost of providing that same level of oversight? And then in the U.S., I'm not sure how this relates to the Israeli market, but in the U.S., the way that the utility companies are structured, they get their rate of return based on the size of their capital base. So they want to capitalize as much as they can. They want to put as much pipe in the ground, and all of the hardware and software associated with that can be capitalized, whereas inspectors and auditors are an O&M expense, and that's just an expense. So they want to, in order to maximize their rate of return, they want to capitalize as much as they can. And technology can be another way to allow them to capitalize something that maybe traditionally would have been an O&M expense. All right, so let's talk, I've got, I think, 3 specific examples that I wanted to talk about how technology can be used to increase the quality of the work that's done out in the field. The first one is related to joint quality. We're specifically talking about plastic pipe. If you remember one of the earlier slides I showed, that first of all, joint failure is one of the significant causes of leaks and incidents. And then Operator error, the joints being done wrong, accounts for 60% of poor joints that are performed. So we wanted to develop some technology that can help with the oversight of joint quality. So we're actually, GTI, partnered with Nortec, and we received a grant from the Bird Foundation to jointly develop some asset tracking and traceability technology that addresses the joint quality. So GTI, we had some technology that used mobile GIS, GPS, tablet computers, and barcode scanning to create high-quality, robust records of what goes in the ground. You use the GPS to know exactly where it's at, and then you use the barcode scanning to capture the asset attribute information. And it's a nice little system that we put together, but what we were missing was capturing the joint information. The barcodes that we were scanning were put on by the manufacturers, and it had material, property, lot, number, manufacturer information like that. But we didn't have a way to capture what was actually done in the field. And so that's where our Israeli partners came in. They have some technology that allows them to hook into the fusion machine and capture those parameters that are important for telling you what kind of joint it was done, what's the quality of it, making sure that it was the right temperature, the right pressure, the right amount of time, all of those important things that can tell you a lot about the quality of your joint. So we've partnered with them, and now we have this system that really creates a full tracking and traceability solution that allows you to map, as soon as you do your installation, you can use this technology to map out your new installations and get all of that high quality tracking and traceability information. So a way that you would use this for quality, for example, you can use it to go back and look at things that were installed. At the end of the day, an inspector could go through and look at the parameters on all the joints to make sure that they were done correctly. Whereas now, very little of that information is captured, and you don't know that you had a bad joint until it actually failed. But now this is a way that someone in the back office can scan multiple fusions, whereas if he had just drove out there, he might only get to see one or two. But now he's got records on everything. Also, if you start seeing failures in the future, you can go back and look at the records and identify what might be the root cause that's causing these joints to fail. The second technology, I mentioned this a little bit yesterday. Very simple concept. It's not that high tech, but it's very powerful. And it's this concept of using smartphones to capture pictures throughout the new installation process. So you identify what steps in the new installation process are critical. What are the things that lead to failures? Maybe it's the joints, maybe it's the pressure test, maybe it's the meter set, maybe it's a certain type of fitting. And if you can identify what those steps are and then require the contractors to take pictures of certain steps throughout that process, that can be a great way to provide oversight. So not only does the contractor now know that someone's going to be looking at this picture, but then you also have a way to, in the back office, to be able to review all that and have some sort of permanent documentation that shows that things were done the way that they were supposed to be done. If you add the cloud computing component to it, this is something that can be done in real time. So one person back in the office can be looking at everything that's going on. They can see the pictures as they pop up, and they can be providing that real-time remote quality control. And again, instead of having one person drive out to 1 or 2 job sites a day, now you have one person sitting in the office looking at hundreds, maybe even thousands of pictures and providing at least some level of quality control over all of those different jobs that are going on in one day. I wouldn't propose that this is a replacement for actually having people out in the field, but I do think it's a nice low-cost complement to having auditors out in the field. So here's a picture of a pilot project that we did with an operator. They identified 5 different steps that they wanted pictures of. They wanted pictures of the pressure gauge at the beginning of the pressure test and at the end. They wanted pictures to make sure the tracer wire was connected. That's a big problem, is that if the tracer wire doesn't work, then you can't locate the plastic pipe and then you have no idea where it is. So making sure that that tracer wire is connected is very important. They also wanted pictures of the job site after it was buried, so you don't have homeowners complaining that their yard is all messy now. So the contractors then took pictures of all of these steps, sent it up to the cloud, and someone sitting back in the office can review all of this in real time. If he sees a problem, he can pick up the phone and call that person and tell them what needs to be fixed. It's all time and GPS stamped, so you know that they're not taking the same using the same picture over and over again. And the last one that I wanted to talk about, GPS-enabled leak surveying. I mentioned this one yesterday as well. The way that so leak surveying, it's a requirement that you walk over the gas pipe with a leak detection device to make sure that it's not leaking. You have to do this once a year. It's mandated that utility companies do this type of survey. And the way that they document it, I'd say 80 to 90% of utility companies in the U.S. get a paper map, and at the end of the day, the person comes and highlights the route that they walk with like a crayon or a highlighter. So this is the country that invented Google and iPads, and we still have people using paper maps and highlighting the route that they walked. Hopefully the technology like this one will help us get past that. It uses GPS to track the routes that they walk so that you know that the inspectors were actually where they're supposed to be. So you can see here, this is those lines represent the underground pipes, and as the leak surveyor walks over them, it checks the box and says, yes, this person was actually walking over this pipe segment. So it provides, this is just another way to, first of all, help keep people honest, and then to have a way to remotely use technology to monitor the quality of what's actually done in the fields. That's all I had. I guess in summary, what I'd like to say is that I think the three things that are important for ensuring the quality of work that's done in the field, it's smart regulations, it's good quality programs at the operators, and then it's the use of technology where appropriate to provide an extra level of quality control. Thank you.